We want to look at different ways to express functions. So g of x, some function g of x can be partially defined by another function. So example here is we have this g of x, it's equal to 2x plus the area under an f function from a to x. And so that f of x can be shown as a graph. So for example here, that f of x, we can define that the integral part of that function by the area under that f function from some starting point a to some point x where x moves back and forth. And we can find the values of that by just calculating the area. Okay, so it can be done like that. That f can be also defined as a function, okay, and we can actually have to integrate that. And in this case here, that would be really hard to integrate as that is a fairly complicated looking function. So we could also describe it as some combined function where in this case, the big F implies an integral. It's embedded inside some other function. And we're going to be expected to use, in this case, it would look like the quotient rule, but we can embed these functions as combined functions. Thirdly, we can have a function, in this case, h. It could be a composite function where we have that function at big F. Again, that implies it's an integral. It could be embedded inside another function, and then in that case, you'd be expected to apply chain rule. So here's an example where we have this g function. It's defined as 2x plus the area under some f function. And we can actually work out values of g based on using that 2x part, but also the area under the f function. So an example here says find g of 16. So g of 16 is going to be equal to, well, I could plug in 16 into the x part of that function. So there's x there, so I'm plugging 16 in. And the rest of that function is going to be defined as the area under the curve from 4 to x. So x in this case is, I'll write this out, the area under the curve from 4 to, in this case, it's going to be 16 under the f function. So that's going to be equal to 32 plus, well, calculating the area under the f function, well, from 4, 16 is going to be right here. Okay, that area, this area in here, is going to be calculated. I'm just going to break this area up into some parts here. So it looks like from 4, that's going to be 7. From 4 to 7, it's going to have a height of 3, so it's going to be 21. This section here is going to be a trapezoid from height of 3 to, looks like 9, so 3 plus 9 divided by 2 is 6, and the width is going to be 3, so 6 times 3, I'm going to get an area of 18. For the next part here is going to be 9 plus, that looks like 6, so 9 plus 6 divided by 2 is 7.5. This area has a width of 6, so 7.5 times 6. That's going to be 45. Okay, so I have those parts there. I'm going to write those in a little bit darker. Okay, so those areas make up that area under the F from 4 to 16. So if I add that up, that's going to be 39, 84. Okay, so 21 plus 18 plus 45 gives me 84. So the value of the g function when x is 16 can be calculated as 116. So we have an ordered pair of 16, 116 on the g function. And that's calculated. We could determine that based on combining these different parts of the functions, the 2x with the area. So that's part A. Part B, it asks to find g prime. Okay, well, for g prime, I need to differentiate that g function. So I'm going to start with a 2x. The derivative of 2x is 2 plus. Now I'm going to find the derivative of an integral. Now remember that we could apply fundamental theorem of calculus here. We don't really need to know what the integral of that function is. We just know that the derivative and integral are going to undo each other, and we're going to end up with f of x. So 2 plus, so g prime at, in this case, it looks like g prime of, oh, it just asked us to find g prime of x. So there it is. That's our expression for g prime of x. We can actually calculate values for g prime. For example, I can say if I want to find g prime at 2, let's make that. Let's do g prime of 4. That's going to be 2 plus f of 4. Well, we can actually just go to the f graph, and at 4, the y value is 3. So we can just say that 2 plus 3 represents my g prime at 4. So that question is a separate question here. We've been just asked to find the derivative, which is going to be written like that. We can look at a function like this. This is a combined function. If we're asked to differentiate something like this, to find g prime, we just need to differentiate the notation. However, this notation is a quotient, so we need to apply quotient rule. So quotient rule is going to look like this. I take the derivative of the top, which is big F prime or f, times the denominator minus the numerator times the derivative of the denominator, which is 6x squared, all over 2x cubed, all squared. And we can then use this expression to do other things. You know, we as long as we can define the f function and the big F function, we can find out any coordinate or any slope on this for this g prime function. In this example here, we have an embedded function. So if I want to find, and not only do we have embedded function, we have the values given in a table. So if I want to find h of 2, what I can do is I can then just plug 2 into that expression. So log big F at 2 plus 1. Well, big F at 2, that's going to be equal to 7, so I can replace that with 7. So then I can evaluate the h value at 2 as log 7 plus 1. This expression we can differentiate. Since it's an embedded function, we have to apply chain rule. So if I want to find h prime, that's going to be the derivative of log, the outside function, 1 over big F. But because f is embedded, I need to find big F prime. The derivative of big F is just little f. And then plus 1, that's just going to differentiate to 0. So now I have an expression that represents the derivative of this composite function h. And it is, in this case, it's going to be the small f divided by big F. So if I want to actually work out this value at 5, I just need to be able to find f of 5 and big F at 5. In this case, it could be a graph. For this particular problem, we have a table. So my table value at x equals 5 is going to give little f is 3, big F is 9. So this is going to be equal to 3 over 9, and that represents the slope of the h function at x equals 5.